So this is our last big theme on a chain of building blocks. We had to know how to put things together. What were the connections? Then we had to know shapes, and we had to know something about polarity, and then we can determine what are the intermolecular forces between neighboring molecules. I'll often shorten this as IMF through my notes. So scientists know that there are intermolecular forces between all molecules. Even hydrogen and helium will eventually transition away from being a gas. Now it has to be really, really cold to get hydrogen and helium to turn to liquids and then turn to solids, but it is possible. So we want to answer the question, what is holding one molecule to another? Okay? The answer is intermolecular forces or van der Waals forces. I'll list them out and then we'll work through them. Okay? I'll use a lot of short forms. The first we're going to look at is London dispersion forces. Okay? Then we'll look at polar molecules that have a dipole. If something is polar and has a dipole, it would be connected to the dipole of the other molecule, of a neighboring molecule. So pluses and minuses attracting each other. So that's our second force. Our third force is really a special type of dipole, but it's called hydrogen bonding. There are 3 cases where we get unusually strong dipole forces, and it gets a special name. But again, these two are the same theory. They're just different magnitudes or strengths. So we'll jump into London dispersion forces first. Good? So London forces or London dispersion forces. So every molecule that we're going to deal with is going to have electrons. Okay? These electrons are really waves, so they're constantly all over the place, in motion in different places. We don't know exactly where they are. They're somewhere in an orbital. Okay? And the random relocation of these electrons will lead to tiny temporary charges. If the electrons are a little bit more to the right of a bond, that side will be a little negative temporarily. Okay. All of this random movement of electrons will create slight attractions between one molecule and its neighbor, even if it has no polarity. So if you have a methane molecule that has no plus or negative end, that's a nice symmetric tetrahedral molecule, and you have another methane next to it. Okay. Every one of those dashes I drew is a pair of electrons. That pair of electrons will create tiny temporary charges and will create London dispersion forces between the 2 blue molecules. I'm just putting an arrow in between. Okay. So temporary slight positives on one molecule would be attracted to slight negatives on another. Now these come and go, they're not permanent. Every molecule has electrons, every molecule has London forces. The more electrons a molecule has, the greater the little pluses and minuses you'll have. So the greater the London forces. So an oversimplification would be bigger molecules have more London forces than smaller. It's not actually the size, it's the extra electrons that a bigger molecule would tend to have. Now, particularly in Chem 30, we'll come back and deal with this more. Okay? But if molecules have lots of branches or fingers coming out and the molecules are far apart from each other, okay, that will weaken the attraction if there's a much bigger distance between molecules. Okay? That's not going to be our focus this year. So I'm going to compare 2 molecules. I'm going to compare London forces in methane versus ethane. meaning 2 carbons. So this is how to be presented on a test. You have to realize that the question is asking what is the forces between one methane and another versus what's the attraction between one ethane and another, or one ethane and a mole more of ethane. So what's going on? Which one has greater force? Okay. The 2 or the mole of methane versus the 2 or the mole of ethane. You don't need to count electrons, just visually, if you look at the 2, the one on the right has more atoms. It's bigger, it's got more carbons, it's got more hydrogen. No need to count electrons, but there is more electrons here, so there will be greater London dispersion forces on the right-hand one. If you compared a molecule with 100 carbons versus a molecule with 300 carbons, the 300 carbon one would have more London forces. Do not waste your time to count all the electrons. You would only count if you couldn't visually tell the difference. 2 molecules look similar. Okay? Maybe water versus methane, you can't tell. So you can just add up all the electrons and the C's, the H's, and the O's and compare them. Okay? So this is our first force. Everything has it. Look at the number of electrons. Now we're going to look at polarity. If a molecule is polar, and that was an important if statement, it will have dipole-dipole forces. If it is non-polar, this force does not exist, and it would only have London forces. So dipole-dipole, we have, I'm not going to use the slight, we have a positive and a negative end on a molecule. That's what I mean by dipole, 2 poles. And that would be attracted to a dipole on another molecule, but it would be flipped. The plus and minuses have to be opposite. Plus and plus would repel each other. So dipole, 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 dipole forces. Okay. A dipole in one molecule will be attracted to a dipole in another. Now these are now permanent dipoles. I talked about temporary pluses and minuses with London. Okay. So we could compare HBr versus HCl and compare their dipole forces. These molecules are both polar. The bromine is more electronegative than the than the hydrogen. So I'd put an arrow towards the bromine. Chlorine is also more electronegative than hydrogen. Now I wasn't careful with the length of those arrows. I just drew them in. I'll have to go back and fix those lengths. Now, how do we determine how polar a bond is? That is the difference in electronegativity. The bigger the difference, the more polar that bond is. So you want to take the bigger minus the smaller. So for bromine, you go to your data booklet. You don't memorize any of these numbers. The number right above bromine in your Alberta data booklet, your periodic table, is 3 for bromine and 2.2 for hydrogen. So that's a difference of 0.8. If the difference was 0, there'd be no polarity. If the difference was 2, you would say this is ionic, not sharing. The HCl difference, chlorine is 3.2, versus 2.2, there's a 1.0 difference there. So there would be greater dipole-dipole forces in the HCl compared to the HBr. Both of these molecules would have two forces. They both have London dispersion forces, and they have dipole-dipole forces. They have two of the three possible forces. Just giving you a little visual of the dipole-dipole interactions. You'd have an HBr, and then another HBr would be flipped the other way around. The negative bromine end would be attracted to the hydrogen end on another molecule. Now this happens in all three dimensions. This type of interaction is what causes those nice snowflake patterns. Water is a polar molecule. So one end of water is attracted to the other, and it can attract and grow as a solid in all three dimensions. On a pane of glass, on a windowsill, or just as a snowflake falling through the sky. So that's two, one force left to do, hydrogen bonding. Now this is still dipole-dipole, it's just a unique one. It's unusually strong. I say it's the strongest, I should say it's often the strongest. London can be really large in a large molecule. So what do you need to have a dipole be called extremely big? You need a couple things. You need a hydrogen atom bonded to a highly electronegative atom that's going to pull a lot of the electrons, not all, but most of the electrons away from that hydrogen atom. And you find we need to have a lone pair on that highly electronegative atom. You have these two things, you'll have hydrogen bonding in that molecule. So our first requirement, hydrogen attached to a highly electronegative atoms. We're going to have hydrogen bonded to something that's highly electronegative. Y isn't a real element, I'm just using it generically. Hydrogen can only have one bond. It has a bonding capacity of 1. So we're just going to see a single to it. This Y could go as many times as its bonding capacity. Okay. So that's going to depend on the group it comes from. Second part, which I'm going to add to the red, we have to have a lone pair of electrons, at least one lone pair on that Y. There could be two, there could be three, but there must be at least one. If we have this situation, we find that this polar bond is extreme. That arrow is abnormally large. It's not quite ionic, but it's getting to be as far as it can be and still be considered covalent, still be sharing. Okay. So 95.5 is still sharing, is not ionic. Okay. So when do we see this? Kind of jokingly as a mnemonic to try to remember this, you can remember that hydrogen likes to have fun. F-O-N. Those are the elements that we see hydrogen bonding in. If we think of what's the highest electron affinity or the highest electronegativity, it's going to the right. These are the atoms that have the greatest attraction for electrons. So they're going to pull that electron density away from hydrogen and have an extreme positive negative and cause the molecules to be extremely locked together, the pluses and minuses. So we got H to O is one of the possibilities, H to N, and H to F. It's just not written out in the fun order, the F, the O, and the N. Now these have to be connected, not just somewhere in the molecule. So the H and the O we could see it attached to a carbon. That's a structural diagram, but I want to add in the lone pairs. It emphasizes the shape and emphasizes the lone pairs that we need to have hydrogen bonding. This is that abnormally large arrow. It's in a bent part of the molecule, so it's always going to be polar. It's never going to get canceled out due to symmetry with oxygen or any of these examples. You could have a similar thing with nitrogen. I'm just putting the carbon in. That's not the piece that has the hydrogen bonding. The nitrogen has a lone pair, and nitrogen has 3 bonds. I'll put in more than one H in this example. It doesn't matter. We have at least one H to N with a lone pair. In this case, we just have 2 of them. Okay. They don't point equal and opposite and cancel each other out. They're both pointing down and left-ish. So they're going to cause an extreme slightly negative here and a slightly positive on the top. Okay. They're never going to cancel. Okay. Last and the most boring, you tend not to see HF show up very often on a test because hydrogen has a bonding capacity of 1, fluorine has a bonding capacity of 1, so I can't attach anything to that fluorine atom. It doesn't have enough bonding capacity. So that's the only HF example. And we have that abnormally large arrow. So you're more likely to see an OH or an NH on an exam. And in grade 12, you do a whole section on OH hydroxyl groups in alcohols. And we'll recap these forces. Okay. And it's worth throwing in water. Water is a small molecule. It's very light. Most molecules of similar mass to water are gaseous. Water is not a gas. Doesn't have to be that cold out, and it's a solid. Okay, where methane would be a gas at -10, water's a solid at -10. Why is a water solid at -10? Because of these 2 hydrogen bonds. This H to O with a lone pair. My top example is 1 hydrogen bond. My bottom has, water has 2. Okay. So we'll end up relating this to melting or boiling points, more forces, higher melting and boiling points, and relate it to solubility. Things that have hydrogen bonds want to stick together, and they'll dissolve in each other. Okay. Something that doesn't have hydrogen bonds will not want to mix with something that has hydrogen bonds. Oil and water don't mix. Water's hydrogen bonds. Oil, C's and H's only are nonpolar. I did water already. I'll just throw up ammonia, and then I've got some practice for you. Ammonia is NH3. Fairly similar to the example we saw before. Ammonia is trigonal pyramidal, lone pair, 3 bonds. All of those are hydrogen. We can get 3 of these large hydrogen bonds in ammonia. They're all pointing up, okay, not canceling. They're leading to a slight negative on the top and a slight positive. Now it's fairly large, but I'm saying slight because it's not a full -1 and a full +1. It's less than -1 and +1. If we had -1 and +1, we're starting to think ionic compound. We're starting to think of an ion now. So I have 4 examples for you to work on. I don't have a heading, but I'd like you to list the intermolecular forces for each. Now I've drawn out 2 of them, and then the last 2 I didn't. So you need to think of what they would look like in 3 dimensions. What's the connections? What's the 3-dimensional structure and shape? What is the polarity? If you're not sure of the polarity, you don't know whether there's dipole-dipole forces. Okay. So good luck, work together, and the answers will go up shortly. So I'm going to put up the solutions for all these, discussing why they're right. Okay. So our very first molecule, I'm not even really going to think very much. Everything has London dispersion forces. It has electrons, random movement of electrons we'll call as London forces. Then we have to think of, is there a dipole? Okay. And there is in this molecule. That carbon doesn't have the same atoms all the way around it. We actually have quite a polar bond there. C to O's are polar. Okay. There's an electronegativity difference. Okay. C to O is given a name in organic chemistry. You won't get the name to university, but they're called carbonyls. So we have a polar section, so there is dipole-dipole forces. That C to O in one of these molecules will be attracted to a flipped C to O in another. Okay. The O is the negative end, carbon is the positive end. Is there hydrogen bonding here? We have an O and we have an H, but the H is not having any fun. The H is not connected to the O. Okay. There is no H to O with a lone pair. That does not exist in this molecule. I'm intentionally trying to not trick you, but see if you really understand hydrogen bonding. Okay. Both of them are connected to a carbon. So that is it for your list. You should only have 2 of the 3 forces for the first example. Our second example is C and H only. Any hydrocarbon that's C and H only, all the bonds will cancel out. Okay. I'm not going to prove this. I never prove it. As it gets bigger, it gets harder and harder to prove. You need to know C and H only is LDF only, London dispersion forces. These are all our non-polar, our oil substances from our hydrocarbons. So don't let the double bond trick you. Okay. Our notes, if you have trigonal planar and the 3 atoms around it, the notes kind of said that it would be polar, okay, but we have multiple central atoms. So that's why the notes aren't working. Okay. We move on to the next example. Carbon with 4 Fs around it. Hopefully you don't need to draw this. Okay. You see carbon with 4 things, so it's tetrahedral. When you have the same 4 things around a tetrahedral molecule, it is going to be nonpolar. So you have a carbon, F, 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 F. Okay. That really doesn't do it justice because it's not flat. Okay. But because the 4 polar bonds cancel each other out, there's LDF forces only in carbon tetrafluoride. So, okay. We move to the last example where there's 3 H's and 1 F. We don't have the same atom all around that carbon. So that's going to make it polar. You don't have to identify exactly where. You don't necessarily have to draw it. But you need to put LDF forces on your list. And because it's polar, there's going to be dipole-dipole forces. Okay. Now that highly electronegative fluorine to the carbon is going to be the most polar bond, and that's going to drive the biggest plus-minus section of this molecule. So those are the 4 answers for the intermolecular forces. Okay. Next is application, boiling points, and melting points. Okay. But that's going to come in the next lesson.